Hello guys, welcome to this module. I hope now you have understood what exactly is TortoiseBot. You have understood how it functions. You have understood at least a crux of it, understanding the gist of it. I've shown you a demo in the previous session. Please, I would request to go ahead and try it out at your system locally. This will give you a brief understanding about autonomous mobile robots. This will give you understanding about how TortoiseBot functions, etc. So if you haven't yet, please go ahead, download, git clone TortoiseBot to your local desktop or laptop and give it a try. With that said, in this module, we are going to dive deeper into understanding what exactly does TortoiseBot comprise of and how it functions, what exactly happens underneath the hood. All that we saw in the demo, we are going to see reasoning for it. With that said, let's get started. So here, this is the git for my TortoiseBot. I'll quickly refresh what's happening. We git clone this and then we build and we ran our package. Now I'll open this via my VS Code. So in my VS Code, I have src and over here I have TortoiseBot. I'll close all the unwanted files. Here we have TortoiseBot bring up, we have TortoiseBot control, TortoiseBot description, TortoiseBot firmware, TortoiseBot gazebo, TortoiseBot navigation, TortoiseBot slam, and YD lidar ROS driver. So YD lidar ROS driver is something that is with respect to this lidar. This lidar is YD lidar X2. So this driver is responsible to run this particular node. But since we are running in simulation, we'll technically have no use for that lidar or for that driver package. Then the very first file we have is TortoiseBot description to explore. This TortoiseBot description has launch, models, and RViz. Inside models, you will find meshes and URDF. Meshes are .stl files. These are 3D bodies that we can render in our gazebo as well as in our RViz. These STL files put up a look onto our robot. It doesn't make our look just a skeleton of TFs. And what are TFs if you ask? I'll get to that. Just hang on with me. These are .stl files that we see over here. Now these meshes further contribute in making the URDF. Now, before we jump into URDF and all, let me quickly tell you what exactly is URDF. URDF stands for Universal Robot Description. I'll repeat that. Universal Robot Description. Now, you must say, okay, it means it's some sort of a description, understanding of my robot. Well, the answer is yes. Imagine it like the skeleton of your robot. Okay, URDF is like the skeleton of your robot. This STL files are like muscles of your robot, and materials that we are going to add further are like skin tone, color, etc. properties. Now, if I have to draw parallels, you must have heard about HTML, right? Hypertext Markup Language. Now, you must say, okay, but that's in web development, that's computer science. Why are you bringing it in robotics? Hold on, I'll give you the example. So, HTML is nothing but a scripting language. Similarly, XML is also a scripting language. Our URDF skeleton of our robot is written in XML language, which is a scripting language. Whereas, HTML is also a scripting language, and HTML is also acts as a skeleton for our website. Further, there is CSS that helps in styling of a website. Similarly, over here, we have STL and materials that help in styling of our robot. I hope these small examples are helpful and these make you understand better. So that's about URDF. Furthermore, we'll dive into URDF. But then we have materials.Xacro. This materials.Xacro is responsible for all the visual material that we pass. Then we have TortoiseBot.Xacro. Now this TortoiseBot.Xacro is your main URDF file. Then you would say, okay, where is URDF? Well, .Xacro is an extension of URDF. It's a format that we write and save our URDF. The entire segment is called as URDF, or the entire part is called as URDF. That stands for Unified Robot Description Format. It's a format to address a detailed understanding of the robot. So now, since we are here, let's dive a little bit further ahead into URDF and why do we need it. So when you see this robot over here, what do you see? Yes, you see there is a lidar, you see there is a camera, you see there are wheels, you see there is a caster wheel, you see there is a chassis on which the entire robot is based and built upon. All of this is like a descriptive answer when I ask, what do you see in my hand? Isn't it? Exactly same thing is URDF. It's a descriptive, detailed understanding about our robot. I'll repeat that. It's a distinguished, very clear and unified understanding, in-depth understanding about a robot. This format is utilized across ROS for describing robots of all kinds. You could be working on mobile robots, you'll use URDF. You could be working on drones, you'll use URDF. You're working on robot arms, you'll use URDF. You're working on underwater robotics, you will use URDF to describe and distinguish your robot in as detailed format as possible. Now, this helps us understanding how the robot is built. It also further helps us in gaining understanding of how different joints and their relationship comprehend the entire skeleton structure. Like for example, this arm is linked to my body via this shoulder joint. This forearm is linked to my shoulders via this elbow joint. Similarly, my wrist is linked with my forearm via this wrist joint. What was this? It was a detailed understanding how my arm or my hand is built into couple of links and pieces and joined together. In this similar manner, we can construct or deconstruct or describe a robot as well. Here, if we'll see closely, this is our base of our robot, the base plate. Now, how are these four plates linked? You can say, okay, this linked via these spacers that we have attached. Then the next question is, okay, how is this camera attached to this plate? You can see there is screws and 3D printed parts over here to connect, link this camera with this plate. Similarly, how is this lidar linking with this plate? You will say, okay, there are screws over here that are screwed on this top plate, and hence you can see that this is how we form links. Similarly, how are these wheels linked to your motor? Well, because of the shaft. Now, all that I spoke right now is nothing but a detailed description about the robot. It also mentioned how the interlinking is happening among different components. Further example, if I have to take, let's say, what color is the lidar? The lidar is black in color. What color is the chassis? The chassis is black in color. What color is the wheels? It's black in color. So on and so forth. What am I describing over here? I am describing visual properties. And again, it's a part of URDF. It's a part of URDF where we have a detailed description not only about physical components, but we also have a descriptive understanding about its visual properties and components. Which means you can definitely alter the visual properties to your liking once you have access to the URDF file, which is written in .xml. So that's a brief understanding about URDF. Now let's see it in action. So the very main file is our TortoiseBot.Xacro. This file starts with an XML tag that says version 1, followed with the very important tag called as the robot tag. You will see that the entire URDF is just between this closing and opening robot tag. So at line number 2 is where we are opening this robot tag, and line number 276 we are closing this robot tag. Now if you're familiar with HTML, this type of syntax will be very familiar to you, and this is a syntax that is majorly utilized for scripting languages. And just a reminder, we discussed about it in our previous modules, that what is a scripting language and what is a programming language. So just to fill you on that, scripting languages are not like programming languages where you have a lot of control flow. They're simply scripts where they have to execute things from top to down in one go. Whereas programming languages have more control flow, have more dynamics, have more detailed control and flexibility over a particular script, like Python, C++, etc. And scripting languages like XML, HTML, etc. So getting back to our TortoiseBot.Xacro, we have this robot tag, that is the first tag that we see, and it takes in our robot name or our robot name space as well. So that is TortoiseBot. So the robot name is TortoiseBot. Then we include couple of other files. This is similar to how we import other files in a segment, right? Or we import a library or we import a module into a different script. It's the same way. Then we have links. Now here the actual story of URDF starts. Why? I'll tell you that as well. See, everything that you see over here, let's say this base link, let's say this right wheel, let's say this left wheel, then followed with caster, that's again a link. Then we have lidar body, that's a link, and so on and so forth. So all of this is a link. So every component that you see is a link. To give you more insights into it, this lidar, this is a link over here. This is my base plate, or also known as base link, as we saw, is a link. This is my left wheel, right wheel. These two are also link. This is my caster. This is a link. This, my camera component, is a link. So what I'm trying to say is every connection that is happening with major components is because these major components are links, and links can then form joints. Basically, my base link can have a joint with my left motor and right motor. My camera mount can have a joint with its respective nearest link. So these individual components are links. These links have their own properties like physical properties, material properties, visual properties, etc. And these individual links can further go ahead and form joints which explain the relationship that I just explained. So earlier I was explaining how my base link is linked with my left wheel, my right wheel, right? How my lidar is linked with my top plate and so on and so forth. That's the relationship that I'm explaining, because every individual link is connected or is forming a joint. And in this way, we can trace the entire tree or entire URDF of a robot, or in another words, the entire skeleton. Now, let's understand what exactly is inside this link. So over here at line number 10, we have our base link. We can see there is inertial properties, there is visual properties, there is collision properties, and we can also see that a mesh file has been passed that we earlier saw. So we see this mesh folder inside our models folder, and inside that we have base_link.stl. Now this base_link.stl is nothing but a mesh file that is being passed as a mesh to represent the visual properties of this particular link. So this base link will be represented in 3D space by this particular mesh file. Similarly, as we move ahead, we have right wheel. This right wheel also has its inertial properties, visual properties, collision properties, and it will also have mesh file, so that in 3D space, this particular wheel link, specifically right wheel link, can be represented. In this way, we have it for left wheel, and again here is a mesh that represents this particular link in 3D space. Now, how important is it to have the inertial and the visual and the collision properties? Well, technically, on an initial level, you just need a link, that is creation of a link. If that particular link doesn't has a specific inertial values, it's fine, but just for getting started. And we are going to see this, how to create a URDF from scratch as well in our upcoming modules. But for now, understand this. These parameters are important but not necessary to start your simulation. Once you start building your end product and you want the simulation to be as realistic as possible, then you go ahead and pass in the inertial and visual properties as close as it can be with the real life. But if you're getting started, if you're just getting started understanding URDFs, building your project, trying to make sense of it, so there is no gains in rushing and adding those inertial values unless and until it is very crucial for your project. For starters, you can begin with bare bones links, create bare bone links, add a basic mesh to it if required, and then start creating joints out of that mesh, which forms a set of relationship between your links. And don't worry, we'll dive into this in our upcoming modules, but for now, let's concentrate on TortoiseBot and let's dive deeper, more further into this .Xacro file. Further, we can see if we scroll past all the links, we then have joints over here. Now, as I mentioned, joints are nothing but made up of links. So every link that we had, that's my base link, my right wheel link, my left wheel link, lidar link, my camera, my motor, my caster, whatever it is, all these links will then form joints with each other to define how they are linked with each other, so that a relationship can be established and we can then determine how to understand and how to describe this robot. Now here, when I speak about relationships of these links, I want to explain you or give you a hint of one more topic that we spoke while we were discussing RViz, is TFs. Now these joints and these relationships with their links is a perfect example and the perfect opportunity for me to introduce you to TFs. TFs, also known as transforms, are nothing but the relationship between two links. And that is also described over here via joints. So next time when we dive or hear about TF, make sure you understand and you acknowledge that TF stands for transforms. And what are they significant to? They signify the relationship between two links. The relationship between two links is transform. We'll dive further into transform when and where it's required. But for now, let's get back to joints. So the very first joint over here is motor right. That is our right motor joint. This is a continuous joint. What I mean by that, let me show you with an example. So this is TortoiseBot. This is my left wheel and this is my right wheel. Here I'm saying I'm forming a joint of my right wheel, which is a continuous joint, which means this joint can move in any direction continuously along an axis. That's representation of my right motor joint, which has a type continuous. Other properties that a joint will have is origin, parent, child, and axis. Now, since this is a continuous joint, we have to provide along which axis is it rotating or moving, or it is continuous. So here you can see 0 along x, 1 along y, and z also 0, which means my wheels have a continuous motion along my y axis. We also see there is a parent-child link that has been created, or in other words, that's the relationship between these joints. So the joint name motor right has a relationship of parent link as base link and the child link as wheel. Similarly, if we scroll a bit down, we have motor left, which is again a continuous joint. As we can see over here, motor left, continuous joint along an axis. Over here, what axis if you'll say? It's again y-axis as mentioned on line 231. Here as well, we have a relationship between our parent and child. Here the parent is base link and the child is left wheel link. So this is how joints are created. Now there are other joints as well. Let's say my lidar joint and the plate. This is a fixed joint. This is not moving. Hence, there will be no axis involved over here. And this type of joint is a fixed joint. Similarly, my caster over here is again a fixed joint. Here, there is no continuous motion. The type of this joint is fixed again. And obviously, these will have its own respective parent and child links as well. So I hope this was a deep dive into URDF, and now you understand what does Unified Robot Description Format means. It is also known as Universal Robot Description Format. You might see this term being interchanged and used a lot, but all it means is a detailed description about your robot. It's a detailed description in terms of how it looks, how it feels, what are the relationships between its components, and how it operates. We'll dive more further and you'll understand how URDF is a very crucial aspect of building a robot in simulation, in hardware, all of it. We'll also dive deeper into other aspects as and when required. I hope this was insightful enough. Go ahead and explore these topics at your end as well. I'll see you in the next one.